Hi, we're going to do a few notes on 3.9 to be ready for tomorrow's lecture. So 3.9 talks about what we call local linearization, which is actually exactly what it sounds like. Local meaning we're looking at a very small part of the graph. So let's consider this as f of x. And linearization means that if we look at that small part of the graph, we can actually visualize it and treat it like a line in a very small area. And the further we get away from the original point, the less that the graph will look like that line. But for getting estimations or understanding what the graph is doing in a very small local area, we can use a line. And the line we're going to use, of course, is the tangent line. So for example, let's consider what's happening at this function at this point, and let's call this point A. So I know how to draw the tangent line at point A. So why don't you guys pause for a second and try and label all the necessary points and come up with an expression for the tangent line at point A in terms of f and f prime. Welcome back. Hopefully what you've already started to realize is that if this is A, then this point over here I can call f of A. And of course, to write the equation of a line in point-slope form, we need 2 points. Sorry, we need 1 point in the slope. So the point we're going to use is x1, y1. I'm going to write our point-slope form this way, solve for y already. And m, of course, is going to be the derivative. I want the tangent line at A, so I can already say that my tangent line y will be f prime at A times x minus, and instead of x1, I'm going to call that point A. And then, of course, y1 would be f of A. And this formula right here is what is frequently referred to as local linearization, meaning it's just the tangent line. We're not actually doing anything new. We're just giving it fancy names. And what we're saying is, in fact, that if I'm close enough to point A, that the function values are, in fact, almost exactly the same as the values on the line. So that's why we write that f of x is approximately f prime, right? F prime of A. Now I want to make that thicker. We'll use green, very pretty. That f of x is approximately f prime of A times x minus A plus f of A, where we realize that this highlighted tangent line equation is just the equation of a tangent line, which is just the equation of a line that we all recognize from algebra. We're just putting in the appropriate notation so it relates to our function, and we would now calculate slope by finding the derivative at that point. Since we have a tangent line, we only have the 1 point to work with, so that's going to be the best way to find slope. The idea is this statement where the function values are approximately the same as the values on the line is really only true for a small area around A. So if we look at a picture here, right, here would be my tangent line. And I can sort of visualize if I take a point right here, the function f of x is now further away from my blue tangent line. So if I use the point on the line, it's pretty far. But if I stay right in here, right next to A, they're pretty close. That's frequently helpful when you don't have a calculator. I can use this because equations of lines I can work out on paper and pencil or sometimes even in my head, whereas complicated functions are harder to evaluate. So that's where this is useful. Let's look again at what some of these things mean on the graph. So once again, I would encourage you to pause and try and label on the graph where f prime of A, x minus A, f of A we've already labeled, all come into play on the graph. All right, welcome back. Hopefully what you guys were realizing is right here, if I call this distance, and this is going to be my distance x, then x minus A, of course, is delta x, right? That change in x is what x minus A represents. That means that this point right here is going to be f of x. So, of course, f of x minus f of A is that change in y. So change in y is f of x minus f of A. And then f prime of A, of course, is going to be our slope, right? So f prime of A equals the change in y over the change in x. So another way I can think about that is we have f prime of A is going to be the change in y over change in x. That's just review of the slope. change in y in our picture was f of x minus f of a over x minus a, our change in x. So notice now I can also solve, and we can express that change in y, just this numerator part, f of x minus f of a, is in fact the same as f prime of a times x minus a. So if we go back up here for a second, we notice here that the change in y right here, I can write as this f prime of a times x minus a. That just represents the change in y. So let's do a problem where we apply this. So let's say, for example, whoops, I wanted to go down here one more time. So let's look at one quick example. Yellow is going to be challenging. If we have the function square root of x, right? Square roots are easy to calculate in our head if I'm doing perfect squares, like what's f of 16, f of 25. But let's say I want to figure out about f of 1.1. That's my goal. And I left my calculator at home and I don't know what to do. So what I realize is if I look at the function square root of x, it looks something like this. And right here, I have the point 1. It happens to be 1, 1. When x is 1, y is 1. And I could imagine that I could find the tangent line. And the tangent line will actually have points fairly close to the real function at, for example, 1.1. So my goal here is to find the equation of the tangent line. And what I'm going to claim is that the values of f of x are pretty close to f prime. I'm going to use 1 for a because I'm drawing the tangent line at 1 times x minus 1 plus 1, right? 1, 1 is my x1, y1. F prime of 1 is going to be my slope. In other words, the function values are going to be pretty close to the values of the tangent line as long as I'm near 1. So all I need to do now is find the equation of the tangent line and then use it. So finding the equation of the tangent line should be review for us because we've been doing that for a long time. So f prime of x in this case, of course, is 1/2 x to the negative 1/2. So f prime of 1 is going to be 1/2 times 1 to the negative 1/2, which is just 1. So the slope is going to be 1/2. So we now have that the equation of the tangent line, which again I'm saying my function value is pretty close to the equation of the tangent line, is 1/2. That was my value of my derivative at 1, which is the slope, times x minus 1 plus 1, because that was at the point 1, 1. So now my objective is to figure out what would be approximately the square root of 1.1. Well, I just plug in 1.1 for x, and that should be approximately the value at the line. So 1/2 1.1 minus 1 plus 1. This is now something I can do without my calculator, where square root of 1.1 is a much loftier task. So here we're going to have 1/2 times 0.1 plus 1, which looks like it should be 0.05 plus 1, or 1.05. And if you do square root of 1 on your calculator, you'll find that it's fairly close. The next question that's frequently asked when you're using a tangent line to estimate is your estimate an overestimate, meaning are you giving a number larger than the actual answer, or an underestimate? Estimates are frequently good enough in science and in engineering. You don't always need to have exact answers. It's a lot of times okay to use an approximation as long as you know what margin of error you have. You can't have an approximation and maybe be off by 10 units. Sometimes it's not even good enough to be off by 1 unit. But if you're using an approximation that you know is off by a maximum of 1/100th of a unit, that might be good enough. And that's where these approximation tools frequently come in handy. And in fact, this is how your calculator is finding square roots and other functions, is by using these approximations with some slightly more complicated polynomials than degree 1, right? Linear functions are degree 1. So back to our original question, here's my tangent line. Pause for a second and consider if we think 1.05 is an overestimate. Here's my, remember I was trying to find 1.1. 1.05 is the point here on the tangent line. So let's consider for a minute if that's an over or under estimate. I would encourage you to pause and sort of think about it and think about how you could explain that. Welcome back. Hopefully what you realized, if you checked it on your calculator, you of course saw that it is an overestimate. And the reason this makes sense is that our tangent line is above the actual graph. So this little spot in green, or most of the green, the distance between the tangent line and my actual function right in here, that distance actually represents the amount of my error. And as you can see, the further I get away from 1, the bigger that distance, the bigger the error is going to be using that particular tangent line. But as long as I'm pretty close to 1, the tangent line is really very close to the actual function, and my answers using the tangent line will probably be close to within 1 or 2 decimal places, which frequently is going to be good enough. This is an overestimate again because the line is above the graph, giving us higher y values when I plug in the same value for x into the linear equation versus the actual function. The next step you should think about, and this is where we'll start the class with tomorrow, or discussion, is how can you tell just from looking at the function, even if maybe you don't have a picture, if you're going to have an overestimate or an underestimate. So that's something to think about.